Hello, I'm Sean Lamp with Danfoss Drive's North American Service Department. Today I'm going to go over how to analyze the data captured by NXS and NXP drives when they have a fault.
Please take a moment now to read the safety warnings shown here. Failure to follow these warnings could result in death or serious injury.
Here I have a service file opened up from a customer out in the field. So we did remove some of the data from here so that we aren't showing the serial numbers and everything of a customer's drive. So as we go down through this, we're going to go down and see in the fault history what faults we're troubleshooting. So you can see in fault history here we got overcurrent faults in fault history, quite a few of them. So overcurrent would probably be the fault that we're troubleshooting here. So you can see it's a fault code 1, it's an overcurrent, happened at 217 days, 11 hours, 6 minutes, 27 seconds. You can see as compared to when this was printed at 223 days, 1 hour, 32 minutes, and 16 seconds. So that was roughly 6 days ago or so, a little bit less than 6 days ago that this fault occurred. That the output frequency was at 51.28 hertz, motor current was 24 amps, motor voltage at 393.3 volts, motor power 52.3%, motor torque at 61%. We were ready, we were running. Direction was forward, we weren't at a fault, we weren't in warning, we were at reference, we weren't at zero speed. DC bus was 769 volts, unit temperature 54. We had a subcode of S1, it was in our power module, and it says it was the V phase. So as we look at this, let's see what data here is correct and what data here isn't correct. So to figure out, probably the first thing we go, because it's an overcurrent trip, we're going to go to motor current. So we see that it's 24 amps that it captured for motor current. Now some of this data we do need to take with a grain of salt. I said this data is sampled at a certain rate, that we don't have enough microprocessor speed that you don't sample this data continuously all the time. That let's say it's every 10 milliseconds that you sample it, because this is basically monitored data. So this is what it's kind of showing on your HMI screen on the front. So when it samples this data, it puts that in the buffer, and when it gets a fault, then everything it's got in its buffer, it throws in this fault history. So if we're sampling this at every 10 milliseconds, there's a time in between there where you're not necessarily going to get true data, that you're going to get data that could be a little bit old, that it's going. So when we're looking at this, we say, all right, what data here do we believe or not believe? When we go into this, the power unit here, and we said this is a PA0735, so that tells us that it's a 730 amp drive, 500 volt. All right, for this drive to trip, it would take about 2.5 times the CT rating of the drive. So a CT rating would be about 650 amps on there. So if we figured that out, take about 2.5 times that, it's right around 2,000 amps. So obviously 24 amps is way too low for that to have tripped. So we know that that pretty much can't be real current. That's not a real current reading, especially considering this drive was pushing 52% power at 61% torque. To get that amount of torque and power, we would need to be up quite a ways. We take a look at what the motor is, that it is a 605 amp motor at 890 RPM. So current limit is at 665. So even magnetizing current on this motor would probably be somewhere in the range of 200 amps. So 24 amps is way too low. That's got to be false current to us. That's not the actual reading. I said we'd have to be up somewhere around that 2,000 amp mark, especially with the power and torque being up there. I said that would have to be probably no less than about 400 amps for it to be that high. Looking at the data and see if there's anything else that we see that might be a little bit weird about the data in here. So going through it, you know, the 51.28 hertz, I said that's about right. I said voltage is about right for that frequency, so that's about correct. Power and torque, I said we don't exactly know if that's correct or incorrect, so we got to somewhat leave that alone for now. Coming down to it, the next thing that kind of looks weird is DC bus voltage. So we're at 769. Now we know that this is a 480 volt unit or 500 volt unit. This 5 tells us it's a 500 volt unit. So typical DC bus would probably be somewhere close to right around 680 volts. So a lot of times in these fault histories, what you can do is you go down and you try and find a fault where the drive wasn't running, and that'll kind of give you what a typical DC bus should look like. So if we go down here, we see we got external fault down here, and you see the drive basically wasn't running here, and DC bus is at 700 volts DC. So I'm going to say that probably about the voltage that is supported by the incoming AC coming into the drive. So when we're running, we probably should be below that level, that it should pull that voltage down a little bit. And as we see all these overcurrent trips as we go through them, that DC bus is a lot higher than that. Here it's 754, 769, 737, 776, 750, 795, so on and so forth. So up here at 769, so we see, yeah, that's higher than what it should be. Temperature, we're at 54C, 49C. This one's pretty low at 28, 30C, but somewhat tells us that maybe the drive does run for a little bit before it trips, that we did get up in temperature a little bit, that we are seeing some time in between these trips. I said 217, 11, 217, 10, so there's about an hour in between these two trips. There's about 3 hours in between these two trips, but they're tripping relatively fast. Assuming that they aren't powered down in between there, that it's getting pretty quick. Get on further here, I said we're getting into maybe a little bit further. You're getting days in between the trips. I said here there's about 4.5 days or so in between trips. Here it's closer to 6, 7 days in between the trips. So you can see the trips are getting closer and closer together as we're getting up here. So we can see that DC bus is kind of high. I said our current in each one of these trips as we go down, the current is low on each one of these, that it's down only a couple amps or so, which we know is almost impossible for what the drive is doing. If it's running the motor, just the magnetizing current of the motor would have to be higher. So with that said, the next thing that we would want to do is if we got the data logs for this, so we would pull the data logs and look at the data logs, because that is more real data in there, that it's what the microprocessor is actually seeing. So this is the data logger for the service file that we were looking at. As you can see, it looks like a little bit of a mess when we open it up. We just got to manipulate this data a little bit to get this to something that is a little bit more readable to us. There's a couple ways of manipulating the data in here to get it so that we can look at things. Down on your bottom time bar down here, if we left click, we can pull that one way. If we right click, we can pull it another way. If we just want to move it back and forth, we click both buttons and we can move it back and forth. It's kind of a slower way of moving things. If you want to do a little bit finer adjustments, I said if we want to lock an area out, because this 0 spot right here, this is where we triggered, so this is generally where we want to start looking for our problem. So the first thing we want to do is relate this to an actual fault. So we're going to look at the time that's on here, this 217 days, 11 hours, 6 minutes, 27 seconds. We're going to go back to the service file, go down, and we're going to find that same time with a trip. And we can see that the last fault in history here was 217 days, 11 hours, 6 minutes, 27 seconds. So it relates to this fault. So this is the data that fault relates to. So we go back to our data logger, and let's find out what went on down here. Now this data logger captures By default, on the older software, it captured 8 things. The newer ones by default captures 9. But the older ones captured, as we go down here, captured U, V, and W current unfiltered. So this is the actual current on the output. DC voltage unfiltered, so we're looking at DC bus unfiltered. Frequency output, motor regulator status, motor current unfiltered, motor torque unfiltered. And the newer data loggers also have a 9th default in there, which is fault. So we don't have to necessarily go back to our service file all the time, figure out what fault triggered here, that it does give us the fault number across there that this actually triggered on. Or I should say triggered on, that it actually happened to the drive, because it did trigger on MC status is what it triggered on.
The MC status trigger value refers to the status word for the software application currently active in the drive. The status word combines various drive status messages into one data word. The bit mask refers to the triggering condition for the data logger to begin saving data. The default trigger, or bit mask, is a decimal value of 8, and, when converted to a binary value of 1000, means that when bit 3 is true, or a 1, a data logger file will be saved. As shown in the example status word chart, bit 3 is true when a fault has been triggered. By default, the data logger file will record 70% of the data prior to the trigger point, and 30% after the trigger. These default values can be changed to values of your choice by using the Tools menu dropdown, and selecting Data Logger. From this window you can select up to 16 signals to record, as well as edit the trigger defaults. To view the status word, some software applications will have a parameter that allows viewing a decimal value from the keypad. If this parameter is not available to view from the keypad, the status word can be read from VACON NCDrive PC interface software. This can be viewed in the monitoring window, and requires the status word to be selected as one of the monitored values. This will also show a decimal value. This decimal value must be converted to a binary value to understand which bits are in a false, or off state, and which are in a true, or on state. The decimal value can be converted to a binary value by using a converter, for example the built-in Windows calculator, or by right-clicking on the status word value box, and then selecting binary. This will open a small window with a binary representation of the decimal status word value. Using the appropriate application guide that matches the software application in the drive, find the status word chart and match the bit number from the chart to the binary status word from NCDrive. In this example, the true states include bit 3, indicating the drive is faulted; bit 5, indicating the emergency stop is not active; bit 6, indicating that run is enabled; bit 8, indicating that power is in a negative direction or there is generated torque, or the current limit is active; and finally, bit 9, indicating that parameter set to is active. The remaining bits indicate the conditions in the false column of the chart.
Triggered on MC status, and the rest of it down here triggered on bit mask 8, which is bits 3. And bit 3 on MC status is fault, so that by default it triggers on a fault. That's what's default in the data logger. And by default it's a pre-trigger of 70% at a sample period of 1 millisecond. So when we're looking at this, we do have 4 seconds worth of data on the screen here. I got to kind of expand it out. If you hit reset scales, it takes it back to the original scale. So you basically got about 4 seconds worth of data, with 3 seconds before the trigger and 1 second after the trigger. Now we're going to expand this out, so let's get up to the top. To make this expand it out quicker, I said we want to take our pointer, move it up, or we don't want to move it up far enough where we get the little bars, because that'll grab the top bar. So that'll grab your top measuring bar and bring it down. We don't want the top measuring bar, so we can go right below that, and then we left click and we can box out an area, and it will expand that area out. Then if we want to bring it in a little bit, we can just use definer scaling to bring that in a little bit. To get our the measuring bar we want to use, we just go down to the end down here, and once we get the little bars up there, we just left click on that and it will pull out our measuring bar. And then everything we're measuring is kind of showing up here. You can pull this wherever you want to pull it and drop it if you don't want it up over on that corner. So we're going to be looking right in this area where it kind of triggered. If we look before it, you can kind of see, I said everything kind of looks normal. I said we're going to measure stuff. We take a look at like our DC bus. I said our DC bus is 709 volts right there. We can see if it gets any higher than that. Yeah, about 709 volts is our highest, and our lowest is right about that point. So we're about 695. So DC bus is pretty steady. Said we aren't very much, there's not much ripple there. 10 to 15 volts ripple, that's pretty low for DC bus ripple. So we take a look at the motor current that we're running. It's, 380 to 410 or so, which is about a little bit over half the VT current rating of the drive. So we aren't lightly loaded, but we aren't heavily loaded either with a 61% torque. That as we're reading that, they said these scales, you got to know what these scales kind of read as you're going down here. The scales, these are based on 1,000 here. That's for the CT rating of the drive. That 1,000 equals 100% CT rating of the drive. The DC bus voltage unfiltered, that reads as it should. That is, you're reading 708. I said that is 708 volts. Frequency output, this here we would put the decimal points in there. You put 2 decimal points in there, so it'd be 51.28 hertz would be the frequency that we'd be running out. Motor regulator status is a bit word. Motor current unfiltered. Depending upon the size of the drive, there might be a decimal point in here, but the size of this drive, there is no decimal point, so that's actually 403 amps is on the output. And the motor torque unfiltered, there would be 1 decimal point on that one. That would be 61.4% torque. So we're running, roughly 61% torque. If we go back to our fault history, according to our fault history, we are pushing about 50% power. So this drive is, loaded to about 50%, roughly speaking. So as we're going along here, we know that the current trips at about 250%. So this would have to get up around 2,500 to be a real current trip as far as the magnitude of current. But as we're going along here, right about this trigger pointer, right before we get to the trigger point, this is where things kind of went wrong for us. You can see our DC bus is starting to rise. All of our currents are starting to drop. Right about that point as we go back, I said right about there, we start to add the currents up. I said as we go back, we know that when we add currents up at any given point, when we add them up, I said we should get 0. Anything that's left over is ground current. So if we're looking at this, we got 900 on one side with 8, 9, 10, 915 on the other side. So about 15, so that's roughly 1.5%, which is really low for ground current. That could easily be a measurement error, but you're bound to get some ground current because you do have common modes and all that stuff that you're dealing with. So we get to this point and we can somewhat see our currents no longer are adding up. So right at this point, we have a negative 200 left over, which is about 20% current. And you can see this is where DC bus is really starting to rise. Now DC bus, anytime you do shut off a motor, will jump a bit simply because you aren't loading DC bus down anymore. That it's going to rise a bit from that, and there will be a little bit of a voltage spike coming back from the motor unless there's a contactor on the output that you're dropping a contactor out, or otherwise you are going to get a little bit of a spike from the motor. But here you can see we do go from, right around 703 volts up to about 805 volts. So we'll say a 100-volt jump, which is well beyond what we would consider normal. That, with the currents not equaling each other, as we can see as we get to here at this point, we got positive 253 with negative virtually nothing there. So we got about 25% current that's not coming back to the drive that we're sending out, that's not coming back. So that's about 25% of what we would consider ground current. So looking at this with DC bus jumping and the ground current being there, we say somewhere on the output, this is going to ground, that we're hitting ground. So what we would start to look at this point is say, all right, with all this happening, you'd have to go out to the motor and take a look at the motor. And we somewhat relate this back to the fault history of the drive also. As we took a look at all these overcurrents happening, you could see when they were first happening, could be days in between where it was happening. I said this was only about 1 day, but here it happened, it's about 3 days, 2.5 days or so. I said here it's about 7 days. Here you got about 5 days, 4.5 days, 5 days in there. Whereas the last 3 of them were happening in hours. I said here you only got about 3 hours, and here you got about 1 hour. So looks like it's getting worse and worse. And this is kind of typical of a motor where it's starting to go to ground, that it gets worse and worse until eventually it'll just constantly happen. So when we're looking at this, we see, all right, go to the output, and start to measure the motor and that kind of stuff to see what's going on the output. Because we can somewhat see, as that DC bus went, if we want to see what happened to DC bus after the trip. Let's reset scales, and you'd see the DC bus did jump, and it kind of discharged back down again here. So that means that we got a pretty good spike in current. And when it goes to ground on the output, so it wants to change the ground reference and kind of rectify that back in the front end of the drive, and you get that spike in voltage on the DC bus of the drive.
Thank you for viewing. We hope this information has been helpful. Danfoss drives can provide additional technical support, parts information or repair services options by contacting us through one of the following methods. For immediate access to customer service or a technical support expert in North America, call 1-888-DANFOSS, or 1-888-326-3677, or contact us by using one of the listed email addresses. Additional information is also available on our website at www.danfossdrives.com. For contact information in areas outside of North America, please visit our global website at www.danfoss.com.